So what I'd like to do is move on to our next speaker. And let's see, do I have my introduction card? No, I lost it. So Eva is coming up here. Eva was, like all of us, confronted with a pandemic a couple of years ago, and she was starting an internship about that. Was it internship or starting an internship about that time, and confronted with data and a need to process data. And somehow or another, she discovered a video series on the internet that was going live, teaching you how to process data, and came at the right time. And we're super lucky that she found it, because she's got some really exciting work to tell us about. So let's see, is it in presentation mode? So Eva's going to tell us about spatial quantification of microstructural degradation. This is a nice temporal four-dimensional study. Microstructural degradation in lithium-ion batteries through Operando. Well, it says through Operando X-ray tomography.
Yeah, I thought this data set was large until I saw Jess's. But like Mike said, it came at an opportune time. And the ability to use a full data set, especially a full Operando data set, was huge, especially in the battery field. Imaging is quite new to the battery field, but we're drawing from fields such as biology to be able to pull in some of those quantification methods. So this was through the Energy Efficiency and Renewable Energy Storage Internship Program, which I conducted with laser pointer here, maybe. Yeah. With Dr. Johanna Nelson-Wecker, who's a beamline scientist at SLAC National Accelerator Laboratory. This was a completely remote internship due to the pandemic, which was all right. I had a great computer at home, so we could really hunker down and ignore the pandemic while looking at these huge data sets. Why do we need lithium-ion batteries? We know that climate change is mainly driven due to our CO2 emissions. And these have risen about 600% since the Industrial Revolution, and as well as further risen or quadrupled into the year 2019 from the year 1990, reaching about 35 billion tons of emissions. If we look at where these emissions are coming from, 73.2% come from the energy sector alone. We break that down further. We can see that 16.2% come from the transportation sector. So to be able to reduce these large amounts of emissions, we really need to turn to renewable energy sources, as well as break into the commercial vehicle market with electric vehicles. And in order to do that, we need electric storage or energy storage devices that can undergo reversible charge and discharge processes for long cycle life. So we turn to here lithium-ion batteries. Lithium-ion batteries versus other recyclable energy storage devices have a higher energy density and higher power density, as well as longer cycle life in compared to these other cells. And this is nearing our combustion engine vehicle, but we still have a long way to go to meet those metrics. So I know we don't have many battery researchers in the crowd, so I want to go through just the internal processes of the lithium-ion battery and of why they are reversible. Here we can look at a schematic of the internal processes of the lithium-ion battery. Basically, the charge-discharge process and these reactions are controlled by the movement of lithium ions in this cell. So if you look at a discharge process, lithium ions are in the anode structure here. So this is just your graphite structure. Lithium ions will then diffuse or deintercalate from the graphite structure, move through this electrolyte, which is basically a salt electrolyte that is ionically conductive but not electronically conductive. This allows for lithium ions to move and then flow through this ionically permeable membrane and then intercalate into our cathode structure opposite of the anode. Since the electrolyte is ionically conductive and electronically insulating, this forces the electrons to move through an outside circuit through this copper current collector, and then move through your device to power the device, and then recombine with our lithium ions in the solid structure through the illuminated current collector at the cathode. So one metric we use to evaluate performance of lithium-ion batteries is galvanostatic cycling. So we're basically applying a constant current and then measuring the voltage, and as well as the capacity of the material. So how powerful is the battery? The discharge process is a spontaneous process. This is governed by our Gibbs free energy equation, which is equal to the negative flow of the amount of electrons multiplied by Faraday's constant, and then the electrode cell potential. So the C rate is defining the rate of the reaction. So how much current are we pumping into this battery? So if I say a 2C rate, this is a 2-hour charge and a 2-hour discharge. Lithium-ion batteries are a really interesting microscopy challenge. We can really evaluate performance and degradation in all different levels and scales. So to give you an idea, I'm going to focus on our cathode structure here. Our cathode material are these spherical polycrystalline agglomerates of these single crystalline primary particles. So these primary particles are about 500 nanometers in scale, and these are agglomerated into these dense secondary structures. And these are optimized to improve your energy density of your battery. The secondary particle cathode material is then mixed with a conductive binder or conductive carbon material, which enhances your electronic conductivity, and then a polymer binder, which holds everything together. And these are cast along your current collecting foil and then assembled into your battery stack. So if we look at the different processes within the battery, from the previous slide, we have two processes. We have the lithium-ion flow and then the electron recombination or charge compensation. These have different pathways in these microstructures. The electrons flow through the solid component, so that conductive binder matrix, into the solid crystal structure of the cathode or our anode structure. The lithium ions alternatively flow through the pore network through the electrolytes. The electrolyte wets through that pore network and allows for the transport of the lithium ions. So then they need to recombine into the solid structure to create your charge-discharge process. And this needs to be highly reversible. So these two pathways need to work in combination reversibly. So if we look at the electrode scale, we see that the current collector is the main electron source. And again, we need the path and tortuosity of the flow of the lithium ions is also important. So as you can imagine, the microstructures at all these different length scales, the density, the porosity, have a large influence on cycling kinetics, rate capability, the initial capacity and cycle life of these lithium-ion batteries. So this leads me to the crux of this project. In order to actually break through into the market with electric vehicles, we need to overcome a lot of issues, such as consumer range anxiety. So the consumer wants to know, how far can I drive on a single charge without refueling? One way we can ease this anxiety is by reducing our refueling times. So refueling, it's really hard to get as fast as a combustion engine. You go to the gas station, refuel your car, but we want to get closer and closer to that time. So the U.S. Advanced Battery Consortium puts out these goals each year in the hopes to fully break through into the market. And they hope by 2023 that we can have a battery pack that undergoes a 15-minute charge time reversibly at 80% pack capacity. Unfortunately, when you go to these higher rates of charge, so if we go to a 3C charge, which is a 20-minute charge discharge cycle, or a 15-minute charge discharge cycle, this can be really detrimental to these fragile microstructures within the battery. This can cause particle fracture at the secondary particle scale. This is due to the large anisotropic volume changes. So as you can imagine, as we intercalate lithium ions in, the lattice will expand. As we intercalate, they'll contract. So the faster that we do that, this is going to cause a lot of strain. This strain can propagate to the secondary particle structure, cracking the particle, and then releasing new interfaces with the electrolyte. This can cause irreversible reactions, which will use up your lithium, and that will directly affect your capacity of your battery. And then at the electrode scale, we can see that the anisotropic volume changes within the cathode structure and gas release through these irreversible processes can cause these voids to form within the binder matrix. So this can cause a disconnect of the active cathode material and the conductive binder matrix, which will electronically isolate that material, reducing your capacity. And this can cause really extreme events, such as delamination of the electrode coating. So that's full delamination from the current collecting foil. So it'll completely shut down the electronic processes within the cathode. So for this study, we're trying to pinpoint these areas of void formation and microstructural degradation. I think I have these. The laser pointer? Okay. Within this 18650 battery. So an 18650 battery is a kind of like your cylindrical cells, your AA's, but just slightly larger. For lithium-ion 18650 batteries, we have these dual-coated cathodes on a current collector separated by your porous separator, and then your dual-coated anode structure. These are wound in a spiral and then put into your battery. So we're using this microcomputed tomography method. This was conducted at the Advanced Photon Source at Argonne National Lab. The higher energy of the X-rays used allowed us to image a small portion of this battery intact as it's being cycled. So we're collecting many tomograms across the charge-discharge cycle. This battery had previously underwent this higher rate of charge and lower rate of discharge. So here's an example of the reconstructed slices as well as our three-dimensional volume. Frozen here a little bit. It's those large images.
Oh.
I don't know. Might have fully, might be doing something.
Is PowerPoint just not responding?
Yeah. Here's that laser point.
Give it oh, I see.
Oh no.
Wake up, PowerPoint.
Oh, here we go.
How about we kill PowerPoint and
Yeah,
start it
read
again?
it again. We're getting the dreaded not responding screen.
If you ever see something like this from our software, well, we're in good company with the Microsoft, with Redmond software.
Yeah. Oh, here we go. Should be all right, hopefully. All right. Actually, I think I'm missing.
I mean, I'm still
think we
going
went-
to close it and restart it if you want.
Yeah.
Okay.
Yeah. So we skipped a couple.
I mean, not that I'm going to do anything that you can't try, but I'll just stand here and project confidence.
Yeah, that'd be good.
Just curious, who uses whose X-ray sources are you using?
So this is the advanced photon source. So a photon source. That's
Okay,
what
okay.
Yeah.
Big old storage ring.
Yeah. And it's being shut down at the end of the week for a big upgrade. So
Okay.
maybe we get some good higher resolution data.
What's the energy capacity
I'm not sure about this one. I wasn't actually at this beam time. I've done a lot of nano tomography work at a different beam line. Yeah, and that one's, we do at 8300 keV or EV, right? Yeah.
All right, so what's the button to tell PowerPoint to present from this slide?
Okay, go up a couple slides, sorry.
Take it away.
Yeah.
Let's see if it behaves. I think this laptop is just underpowered for your overbearing data.
Yeah. Let's see if it'll. All right, cool. Yeah, so this is probably the first conference I've spoken at where I don't need to go fully into what segmentation is, but we are using a semantic segmentation method to be able to fully quantify this data. And as you can tell from the grayscale data from this XC slice, we have a lot of overlapping intensity values. So to hand segment this data, like Jess alluded to be really impossible. I timed myself while making training data. It takes about 20 minutes per data slice to be able to hand segment fully these 6 segmentation components. And there's about 1,024 components within, or slices within this 3-dimensional volume of a single tomogram. And then I collect about 20 to 30 tomograms across that charge-discharge cycle. So what we're looking at here is our cathode composite. So this is your secondary cathode materials with your conductive binder matrix. And then we're analyzing these cathode voids, so the voids that have formed within the conductive binder matrix. And this is, we found these voids in comparison to the as received or uncycled data. And then we have our aluminum current collector sandwiched between these two cathode composites. And then our anode structure, which is darker here, our graphite structure, and then the anode voids, as well as our really bright copper current collector. So here, returning to our deep learning segmentation method to be able to fully quantify this data set. And really, it only took 17 slices of data across our Operando data set. This is a really nice data set because we have really clear repeating layers. So it really performs well in this type of data segmentation workflow. But it takes about 1 hour of automated application of the model onto a new tomogram. After the data segmentation was complete, we want to find out where these voids and degradation is occurring within these electrode layers. So I'm using this spatial identification technique called Euclidean distance mapping. Mike Marsh has a really great video on that on YouTube. I've used this a lot in my research, but basically for this project where you use a segmentation reference point, so one of your components is a reference point, it creates this three-dimensional gradient map where increasing distance away from the reference point, it corresponds with an increasing color of pixel. And this pixel color is then normalized to your pixel spacing, which gives you a distance measurement. So here we're using it to identify these voids within the electrode layers, but I've also used it in single particle research with the nanotomography and elemental specific tomography and looking at elemental gradients within particles. So we can look at both the secondary particle structure as well as primary particle structures and see where these elements are falling. So all of this data was from the reconstruction before and then implemented into Dragonfly, created training data, and then implemented the model on the new data set and did all the analysis through the Dragonfly software. Here's just an example of the training data set. So one slice of data, the different components being segmented, again, 17 slices, and then here's the data output. So it's very close to what the hand segmentation looked like. This is better visualized in the full three-dimensional set. Here we can see our repeating layers of dual-coated anode and cathode with our corresponding current collectors. Now we can peel away the structures of the anode-cathode composites to better visualize the voids that have formed through this higher rate cycling. Here's the aluminum current collectors in green, and we have our cathode voids in orange here. And then we can do the same for the anode structure. Here, anode and the copper current collectors. Peeling away the anode structure, you can already see a higher localization of anode voids as well as a higher amount of anode voids in comparison to your copper current collectors or your cathode structures. To evaluate the model, we're just using intersection of union score, F1 scores, and then a whole suite of other common deep learning segmentation error scores. So this is basically your ratio of your true positives over the sum of your true positive plus false positive plus false negative. I also created these error maps, which basically shows the position of any false positives and false negatives in comparison to our ground truth data. So this is basically just your difference between your hand segment and ground truth and the data output. It's hard to tell here, but we have very minor error within the boundaries of the segmentation components. So this allows for you to adjust your measurements of what you're pulling from this based off of that information. But overall, performed very well to the point where we can trust this model. The only segmentation component, such as the cathode voids, performs slightly less, though these measurements are dependent on pixel value, and cathode voids were the least amount of pixels associated with that class. And then again, we're using Euclidean distance mapping to be able to identify spatially where these voids are formed. Another metric that we use this for, though, and this wasn't something that we were planning on doing, but it really flowed nicely, is measuring electrode thickness. So electrode thickness is a really a great metric to indirectly observe capacity retention of the batteries, and reversibility of these charge-discharge processes. Again, as we intercalate lithium ions in, we're going to see expansion. Deintercalate, we're going to see contraction, and this happens at the electrode layer. One thing that battery scientists often do is measure this dialitometry using externally measured setups where you use a soft-walled pouch cell, so a pouch cell that you'd find in your phone, and you can only use one electrode versus a strain-free electrode, so lithium metal electrodes. You can only measure one component at a time using this externally measured dialitometry experiment. But for using the Euclidean distance mapping with microcomputed tomography, we can then, for the first time, measure electrode thickness of both the anode cathode, deconvolute the contributions, as well as figure out, we can use different cell architectures such as these 18650 cells where the geometry is really complicated, or more hard-walled cell architectures. So in this case, for both the positioning of the voids as well as electrode thickness, we're using the corresponding current collectors, which are sandwiched in between the layers, as our reference point to calculate our Euclidean distance transform gradient map. This is really nice because it follows the contour of that spirally wound cell. And we're using this mean value of distance to negate some of that error around the boundaries of the segmentation components. Here is the data of the dilatometry. We can see the anode and cathode expansion contraction graphs. This is the third through the fourth charge, so earlier on in the cycling experiment. We can clearly see in the anode structure contraction at about 3.7% upon discharge, and then returning about 99.95% of the original thickness upon charge. We can see high reversibility even in the 80th to 82nd charge, even though at this point in the battery, we only have 80% of the original capacity remaining. Something really interesting and confirmation of the resolution of this type of measurement is that we see these dilation plateaus. And this is confirmed in the externally measured dilatometry experiments using a graphite anode. We have different staging compounds, which are defined by the amount of lithium that goes in the structure. And you will see this plateau in expansion upon discharge and charge, though we have a higher rate of charge here, so it's not as resolved. The cathode structure, it's a lot more noisy of data, but we generally see the expansion contraction and the reverse relationship as we would expect in the charge-discharge process. The noise of this data is partially due to the anisotropic volume changes the cathode undergoes. So if you insert lithium ions in the cathode lattice, we'll see expansion in the C-axis, but a contraction in the B-axis. So not as clear trends as a graphite layered structure where you see very clear linear expansion. But also lower segmentation, ability to segment the aluminum current collectors since you have lower contrast compared to the high energy of the copper current collectors. Here is just a video of the aligned data set so we can clearly visualize the expansion contraction of the anode with the actual measured graphs. And I should mention that each data point along this charge-discharge curve, each data point along the x-axis is a single tomogram. And then each data point at each of these points is a single layer of the electrode coating. So through itemization, we can clearly separate the layers and then find some positioning that way. Since we proved we can track the expansion contraction of the anode cathode structures, we can then go on and position these voids that have formed due to the higher rate cycling and where they are in relationship to those current collectors. So visually, we can clearly see a texture difference from the as received state to the higher 82nd charge state. Clearly increase in voids. And then with the Euclidean distance mapping, we can clearly see a strong localization of higher volume voids within the first 5 to 10 microns. These localizations then grow upon further cycling. So this can hint at that delamination effect happening, which would shut down some of the capacity of the battery, as well as we see the voids along the body of the coating further increase as we go to further cycling. Looking at this histographic data, which is ordered by anode void volume, we can clearly see again this increase in void volume, as well as we also see this expansion contraction of the void network upon the expansion contraction of the entire electrode. For the cathode, visually it's harder to see the trends, though we do pick up a decrease in initial voids from 0.97% to 0.4%. So this is in direct opposition of the anode relationship where we saw the increase in voids. The cathode structure is optimized to have initial porosity. So any particle cracking has been seen to reorder the structure and fill those initial voids. So again, that could shut down some of the lithium ionic transport. Here we see more even voids formed along the entire body of the coating with some localization within the boundary, which could be due to some segmentation error. Harder to see, but we do see overall increase across the entire body. And then looking at the histographic data, we clearly see that decrease in void volume. And then again, that expansion contraction of the void network with the electrode layers. So some conclusion. One of the great things that came out of the study is the ability to track these dilatometry trends in a hard-wall cell architecture. So this gives us a lot more freedom than we had previously. So when we're looking at different anode materials like silicon, so silicon will expand to a much greater extent than our graphite structure. This is going to be a huge metric when that research moves toward these higher density batteries, such as cylindrical cells. We saw highly reversible expansion contraction of anode layers. And then we saw this overall decrease in cathode voids with a corresponding increase in anode voids upon cycling. And then showed this higher localization of voids within the anode layers close to the current collector, which could hint at your delamination of your coating. And then cathode voids remain dispersed. So I'd like to thank my thesis advisor, Dr. Joy Cabana. So I defended my thesis back in June 2022. So I couldn't have done it without him, as well as Dr. Johanna Nelson, who was on my thesis committee and also was my advisor through this project. Beamline scientist, Dr. Jingjiang Zhao, which he helped with the microcomputed tomography collection, as well as, of course, Mike Marsh. I couldn't have done it without those videos, to be honest. I mean, it's very inspiring. This project came perfect timing with those videos. So I've used it a lot in my research. So thank you.
That's some really terrific work, Eva. I want to say a couple of things. So first, I want to compliment you on all the data analysis and data tracking. In the dilatrometry, not only were you able to measure the thicknesses, but you're tracking individual layers and convincingly and effectively communicating how all the layers are changing. So you're not only analyzing dozens of tomograms, multiple layers within the tomogram, and then tracking it all and presenting it all. So it comes together as a beautiful story. I don't know how you did all your data management, but it's
tough.
Very impressive.
Yeah. Many session files.
And the other thing I'll tell you is all the X-ray CT hardware maker vendors in the audience are all salivating at your talk because they're all right now figuring out how they're going to sell more laboratory X-ray CT to the emerging battery production and inspection market, and they're also salivating at your data because with the laboratory CT, when you have a layer that may be 50 pixels thick, they're only seeing 5 or 6 pixels thick, so it's very exciting work. But we're going to keep being late because I'm going to keep talking, so sorry about that. Let's go to you guys. I'm sure we have lots of questions. So we'll start with the X-ray CT maker from Nikon, Josh.
Cool.
I'm salivating a little bit here.
Nice.
Though I did want to ask quickly to yourself and all the Dragonfly people here. On slide 14, I noticed some pretty prevalent ring artifacts in that scan data. And I was wondering kind of what can Dragonfly do? Because it doesn't look like they are eliminated or minimized in that one. And of course, having rings in a jelly roll is super fun.
Yeah,
So
right.
I was wondering, can Dragonfly use ring artifact minimization, or what can it do?
So the question is, and I think it's for Eva. If it's for me, I'll take it offline and I'll somehow answer the Zoom audience as well, but I don't want to take up Eva's time. The question is, when we see ring artifacts we'll talk about later what they're from. When you see ring artifacts, is there something you can do about them in Dragonfly? Are you doing anything about ring artifacts?
Yes,
And you might mention what reconstruction toolchain you're using.
Right, yeah. I'm just using handwritten Python code using TomoPy Astro Toolbox to be able to reconstruct these. I did mess around with the ring removal algorithms. What I found was that really messes up the deep learning segmentation. I counted for the ring artifacts in the segmentation, so I was able to identify that as not a void. Though earlier versions of the model, it was picking that up. So I really use those error maps of false positive, false negative to inform not only what the deep learning model is doing, but inform how I'm segmenting the data. So earlier on in the process, I was over-segmenting. So I realized I really need to go to under-segmentation of the void structure, especially to be able to actually get the data that I want and make sure it's picking up only the voids.
I would love to talk to you for hours about this because how you can differentiate a possible crack in a cathode from a ring artifact is incredibly
tough.
Interesting.
Yes. Yeah.
Well, thank you.
So now we're going to throw to the Zoom audience. Eric, if you'll read the question for the room, and then I'll read the question for the Zoom audience.
The question is, do you use an analytical relationship between the mean EDT distance and the layer thickness to compute layer thickness from the distance sample?
Do you use an analytical relationship to infer something about distance maps and position? I guess I lost it. Did you get the question?
I think so. Yes, I mean the mean distance was since we're communicating this data as a percentage. So yes, you're not getting the exact thickness using the mean, but you are getting the change in thickness using the mean. I was originally using the max distance, but it's going to pick up that boundary area. Yeah. And it's not going to be, it wasn't as good of data. This clearly showed the change, though you can get general, like maybe starting thickness and then use that mean percentage change to calculate that based off of that. Yeah.
Another question from inside. So we'll go right here. Hubert?
It was really good talk. I was wondering, like, when you do discharging and discharge, you must have like a temperature, right? So you have the dilation of the layers that comes from the discharge, but also you have an effect coming from the temperature, I expect. So can you like separate these effects in the study? Like, do you have like a active cooling on the battery to avoid that? Like, how can you, because you have dilation from the
The question is, when you see thickness changes, is there any way in your analysis for it to be separable between contributions from temperature versus contributions from chemistry?
Yeah, I mean, that's a huge problem in batteries. We see battery pack fires all the time in the news. So that's something that we're trying to account for, and something to be able to see in these degradation processes and contributes to these voids forming. To deconvolute them into the tomography data, I have not done that. I'm not sure how you could do that, maybe heat signature mapping, but it contributes.
Maybe from a battery researcher perspective, you may need to know whether it's swelling or not. You may not need to know whether it's swelling from heat increase in temperature or from chemistry. You just need
exactly.
to.
Yeah.
Yes, right here.
Hi, this is Ken. So actually, I also worked in Argonne for a few years.
Oh, nice.
By the way, is this from the sector 13 or which?
This one was 2BM. I've done a lot of nanotomography work at 32 IDC, though. That's my main work.
But sometimes there are some dust in the mirror and cause this green artifact. Some of them.
Yeah.
And I have one question. So the anode, did you ever try to analyze the size of the particle in the anode?
Have you tried with the nano CT to analyze anode particle size? So that's in the graphite?
Yeah. Well, obviously, this technique, you cannot see the individual graphite particles, but actually, Mansi Poral will have a poster later looking at exactly that, using a nanotomography method to look at the individual graphite particles within the structure. So she'll be took over my research project in Jordi Cabana's group, so definitely check that out. Definitely need a higher resolution technique. I've done a lot with the cathode side, so measuring size, shape, pore distributions within secondary particles, and then most recently elemental gradients. So we just published a paper in ACS Energy Letters showing that in single cathode particles.
All right, let's do one more question, and then go ahead and hear it in the back.
I have kind of a bit of a philosophical question in terms of where are we going into the future with this energetic transition. We see manufacturers of batteries trying different forms. They do cylindrical batteries, they do pouch batteries, they do kind of bricks batteries, prismatic batteries.
Yeah.
So from your knowledge, what factor form is the most offensive to pack energy and to be safer from these types of batteries?
So the question is, can you speak at all to the form factors of how the jelly roll batteries are actually manufactured, like the prismatic cells, the pouch cells, and the cylinder cells?
Yeah, I had an internship as well as Argonne National Lab at the Cell Analysis Modeling Prototyping Facility, which is exactly that, trying to find the right format for different battery chemistries in different cell architectures. I think it really depends on chemistry and the electrode processing. You'll see different car manufacturers use different formats. I know Tesla uses the cylindrical cell, whereas Chevy Volt uses the large pouch cells. So it's really dependent on the car battery manufacturers. And you see very different internal, how they assemble these batteries. So since my PhD, I've returned to Argonne as a postdoc in the battery recycling group, ReCell. So using some of these imaging work as well as cathode synthesis to be able to identify ways of recycling these battery materials. And something that they found in the separation side of battery recycling is that you have all these different configurations from all these different companies, which further complicates battery recycling. So it seems like there's really no standard out there, which may be something we need to reckon with in the future, especially if we're leading to more better recycling.
Is the 18650 the closest we have to a standard where people are using, or is it
Yeah.
because the cells may be standard, but then the assemblies are non-standard?
Yeah, exactly. Yeah, the cell shape is standard. We have our 1860s, we have our 40 somethings. But yeah, so the spherical or spiral round structure, that's pretty standard. When you get to pouch cells though, you have very different stacking.
Well, okay, so I'm going to keep us moving along. I'm responsible for the delay, and now I've got to try and get us on track. Let's thank all of these speakers again from this morning. This was